Hello fellow problem solvers, so today we're going to be doing a problem from the 2021 IMO, problem number 5. I suggest you try this problem out for a minimum of 45 minutes, ideally 2 to 3 hours, but not more than 4 hours. If on the other hand you'd like to go along with us, I suggest you take a preliminary look for the next 20 minutes and also play around with the problem at the same time. So now, without further ado, let's begin. So this is what we have. We have 2021 walnuts, W1 for W2021. They are on a circle in some random fashion. And on the kth move, we switch the neighbors of the walnut k. So if we have this, we will have this later. So WA, WK, WB will have WB, WK, WA. And we must prove that at some point we'll have A less than K less than B or B less than K less than A. Now, there are two major problem-solving strategies employed here, and one is specific to this problem, and one is generally for these types of problems with 2021, where a huge number of things that are changing and taking place. And the strategy is that the first one is play around with small cases, but here 2021 might be important in some way. And it can be important because of its divisibility by 2, perhaps, because we're switching 2 walnuts. Divisibility by 3, because this is a process that takes on 3 walnuts, or maybe even divisibility by 5, though that's less likely because there are also these adjacent walnuts to WA and WB that are having new neighbors. So those might be some things why 2021 is important. And the way we can figure out which one of these it's important for is by playing out with, instead of W, like 2021 walnuts, we'll play around with n equals 3, 4, 5, 6, 7 walnuts. And we will see in which cases does the problem statement necessarily hold true, and in which cases it doesn't. And if in some cases it doesn't hold true, that might also give us a hint as to what's 2020, like why is 2021 important here. So now if you haven't already, I invite you to take 10 minutes to maybe even 15 minutes or 20 minutes to play around with n equals 3, 4, 5, 6, 7 and see what it is you notice, what it is you find. So first for n equals 3, we just have W1, W2, W3, and these change. Like this will definitely happen when we get to W2 because W1 and W3 will be exchanged. Now, of course, I forgot to mention that there's a third option, which is that it's just the size of 2021. Like maybe starting from some n, this thing always holds true. So maybe it's the size, but that is a thing that we will find out by playing around. Namely, for n equals 3, we see it's not about the size. It's not just about the size, but there's also something here. Now, it may be that in the middle, numbers don't follow this rule, but let's play around more and see if that's the case. So now for n equals 4, we have, say, W1. Okay, if W2 is next to it, what do we have? So those are maybe like the two cases. One is with W2 next to it. The other one is with W2 opposite it. And then we have W3 and W4. It doesn't matter where. If W2 is next to it, then we have two cases. One is where it's W3, W4. And the other one is W2, W4, W3. I think these are all the possible combinations. And I'm checking it out. And I think it is true that these are all the possible combinations because it's like the first one you choose. And then you have 6 options for the other 3. But due to symmetry, you can divide by 2. And now let's play around with every single one of these cases. So for this one, say, let's call this A, this B, and this C. So what do we have for A? We have A. We'll move on to W1, W2, W4, W3 with W1 started. And then W2 will exchange W3 and W1. Then we'll move on to W3, W2, we played with it, and 4, and then we'll move on to, so this seems to be the case in this one. We will switch it in A. Let's see if we'll switch it in B and C. In B, we'll have W1, W3, and W4. Then we'll have W2 with W3 and W4 switched again. And then we'll have W3 switching around these two. Oh! So this is important for n equals 4. This is not necessarily the case. Now, when you play with some cases for n equals 5, you see that it actually is the case that every single time you will have this sort of switch, like this sort of thing happen. So for n equals 5, it is the case. For n equals 4, it's not the case. For 3, it is the case. Right now, my intuition is because for 2021, this is 2 mod 3 and 1 modulo 2. It's either a modulo 3 thing or a modulo 2 thing. Though truth be told, we haven't tried 6, But once you try 6, there is a case, I believe, where it will not work. And that case isn't too difficult to come up with. It is W1, W2, W3, W4, W5, W6. And now you can also find a general case for even n that fails. So now this tells me that it's not about modulo 3, but something about modulo 2 that makes this not necessarily be the case that we'll have this, but for odds, it is the case. So what is that? And now if you want to try something on your own before I tell you the next problem solving principle that is specific to these types of problems, I invite you to pause for another 20 minutes and play around with it. If on the other hand you'd like to principle, here it is. So if you watched my videos before, you may have come across this principle that if there's a change, look for things that stay the same or change in a predictable or controllable fashion. So for our problem, there is a change happening. There is this switching of walnuts. This WK, WA, WB switching to WK, WB, and WA. And there's a change happening. So what is not changing, or what is changing in a controllable manner? And what is it about this process of change, the thing that's changing, that's forcing evens, like not forcing it, but allowing evens to not have the situation where A is less than K is less than B, or the opposite? What's allowing evens to have the ability to get around that, and odds that need, and what's forcing the odds to have that? And now comes if you want to work with this principle, now here I invite you to pause for another 15 minutes and play with this. Try to find something that's not changing or changing in a controllable manner. And here's what I would be doing now. And the thing is, okay, so we're looking for something that's not changing or changing predictably. Let's take a perspective shift. What is the problem statement saying? K less than A, greater than A less than B. What does this mean? That means at some point we'll come across a walnut such that one of its neighbors has been this, I don't know, let's call it pivot, and the other one hasn't been the pivot. So WB hasn't been the pivot. Now let me just circle around the pivots just to keep track of them. And that's really what the problem condition is saying. The problem condition is false if at every point either both of neighbors of the K have been pivots, or both of them have not been pivots. So that is what the contrary of the problem statement is. So now to actually play with this idea, one thing that we could do is to count how many times it has been that these neighbors are different, how many times they are the same, they've both been pivots and they both haven't been pivots. So for example, for n equals 3, we have W1, W2, W3. So first one is a pivot. So let's do this as both greater than being different, and the other one is both being less. So they're both greater, they're ones. With W1, they're both greater. With W2, they're going to be different once. And for W3, they are both going to be less. So it's 1, 1, 1. Now let's look at a case for n equals 4. Let's say W1. Say this case that actually fails. What do we have? We have, okay, it's going to be greater once, I think. Now twice, it's going to be greater than. So twice it's going to be greater than. And then twice it's going to be less than. And it's going to be different 0 times. Let's look at another case where it actually doesn't fail. W1, W2, W3, W4. So now they are different once, and then we'll have W2 and W4 different twice, W3 and W1, and now they are different 3 times. Is this correct? Wait a second. Let me just double check this. Actually, wait, for W1, they're both greater than. My bad. W1, they're both greater than. So once greater than, 2 times different, and 1 times they're both less than. And in the final case where we have W1, W2, W4, W3, we have both are greater than once, and then W2 and W3 change, and then we have a difference, and then again a difference, and then W4. So we're again having 1, 2, 1. Okay, now for n equals 5. Say we look at W1, W2, W3, W4, W5. What happens? So, okay, there's 1, 4. Now we're going to have 1, 4, both greater. And then we're going to have 1, 4 different. Then, because this is W1, W3, W5, so W3 will have a difference again. And then we have both that are less than. And then for W5, we have both which are less than again. Let me double check this. Yes, that sounds good. So it's 1, 2, 2. And then we can look for other types of examples for W5. And here, if you played around with this sort of setting, I invite you to pause for 5 to 10 minutes and figure out, would you like to go play more with this sort of invariant, like, or not invariant, but a monovariant, looking at how many are different, how many are greater than, how many are less than, when these changes happen, and seeing what does it mean for there to be 0 different. And here's the next step. And as with all monovariants or invariants, whether or not they work really depends on your own judgment. For me, I still want to see what happens if there are 0 different, and then like how many greater than, how many less than are there? Like, is there some relationship between them? If I have 0 difference, if I only have both A and B that are less than K, or A and B which are both greater than K. So now let's explore. Let's see, okay, what happens? Let's say, let's look at the great then, there to my left. And then we'll look at the less than if we don't figure anything out. So for the greater than, that means when we are switching K from A to B, when we're switching A and B, then neither one of them have been used before, okay? Now, can we say anything about A and B? Well, just from the fact, are they, now I'm asking myself, K is now a, a great. K is a great number. Now, do A and B have to be lesser numbers? Like, because of K? And now I'm thinking about that. If this has like some K plus some constant C that's less than A, then we'll switch this, and then A will be moved here. And then we'll have both numbers. Some T and A will be here as well. Oh, so, okay, so now this is a thing. If K is great, then A and B will both have to be less, right? Because let's assume they're not less. Well, if they are not less, then at some point they have been switched from a great number. They've switched, but by our hypothesis, they've been switched from a great number by another great number, which is less than them. So they will just have to be less than. Okay, this is cool. And now I invite you here to pause for another 5 to 10 minutes and see if you can push this forward or not. And the next idea is, well, what does that mean? That means at the end of it, when we have the great numbers, every great number will be surrounded by 2 less than numbers, like 2 lesser numbers, like lesser and great numbers. So what does that tell us about the number of great numbers here? Well, if you look at 5, at least that means, so see, we have great, then we have 2 less thans. Then the worst is if case we have another great and then another less than. So that means we have sort of a limit on the number of great numbers we have. And I think the worst case, I think we can prove this, is that when you have G, L, G, L, G, L, wait a second though, for every great number we have some less than numbers. What if we just have one great number and every other number is a less than? I mean, that can't possibly, it doesn't seem like that can be the case. Well, wait a second. So we have this sort of thing. Every great number will be surrounded by 2 less than numbers. And now the question is the converse true as well? And it seems like it is, but let's actually try to prove this. So if we have a number k, that's now less. So both a and b have been tried before. And we'll go from kb to kba. Now, is it possible that either a or b is greater? Well, at least one of them, when we played with a or played with b, I mean, I think exactly one of them, had to move k, and k is greater than, so at least one of them is a great number. Okay, now that's interesting. Now, is it possible that the other one isn't great, but rather that it is less? Let's check that out. So if, say, we have k is great, and actually k is less, we're looking at that case, k is less, and a is great. Okay, so it means that at some point we had a, k, l, where l and k were both greater than a, and then we did a, and then we switched them. But also L here, like we did A after we did B. So that means B gave us the L. So before A and B were touched, we had A, K, we had B, we had L, and we had some T. And now, what do we know about these numbers? Well, we know that B is less than A because it's later down the line. We know that K is greater than A, and we know that A is a less than number, which means T is also greater than A. Now that also implies that because T is greater than B, that implies that L is greater than B. Okay, so this is actually very cool. Now we have for every less number is surrounded by 2 great numbers. Oh, I mean, actually not surrounded by, but when the switch happens between 2 numbers that are less than that, both of those numbers need to be great. Now here's a point where I need to double check my reasoning, and I invite you to take 5 to 10 minutes and double check your reasoning as well. Even try to maybe finish the problem if the reasoning is correct. So the way I would check this is saying, okay, what am I claiming? I'm claiming number 1. Every k that is great will switch to less numbers, or to numbers that are less. And every k that is less will switch to numbers that are great. I'm claiming these two things are true. And then I'm claiming as a result of this, every great will be surrounded by 2, will be around 2 less at the end, and every less will be around 2 greats. and this will lead to a contradiction. And if you remember the case for the thing that actually did not satisfy the problem statement, W1 and W2, you switch them around, you get this situation, then you switch W3 and then W4. Both W3 and W4 are less, both W1 and W2 are great, and you have GL. And the reason this will lead to a contradiction is because we can't, that means, what does that mean? That means we have a GL type of situation, well, it's L at the end, but we have an odd number of numbers, but this would necessitate that we have an even number, because for every G you have an L to the right of it. That's really what it means. And for every L you have a G to the right of it. And that sort of thing just necessitates, we can pair them up, and if there's one G that's unpaired, then that G, no, it can't be unpaired. Every G has an L to it, and every L has a G to the right of it, and then we have an even number of G plus L's. And I believe this sort of reasoning will solve our problem. And now maybe let's actually try to formalize this and write up a solution. But before I do that, let me also tell you about the second solution, the second invariant that you could have figured out. And that invariant is really, say that after a donut has been a pivot, then again, what are we doing? We are assuming that at every point, a walnut that becomes the pivot has 2 non-pivots aside it, or will have 2 pivots next to it. And now what you can calculate is the number of neighboring pivots. How does that change? So here, in this case, it went from some n to these 2 switched around, and this one becoming a pivot, to nothing. It didn't change, changed by 0. But here we had a non-pivot and 2 pivots, and then we switched them around, and this became a pivot, and now we have 2 extra pivot neighbors. And with those 2 extra pivot neighbors, we have that, number of pivot neighbors changes by 2. So it changes by 0 or by 2. At the beginning, there's 0 pivot neighbors. At the end, how many do you have? You have 21 pivot neighbors. So this is a contradiction just by parity. But now let's actually take the time, and this is a solution. And now let's actually try to write up our different solution with these great and less numbers. And if you haven't done this, I invite you to take 10 to 15 minutes and try to put all of this together and write up a solution. That's what we'll be doing now. So we first set it up, assume the contrary, call walnut k great and less if A and B are greater than it, and less if they're both less than it. And now we move on to our claims. So the first claim is a great walnut will switch to less walnuts. And the way we prove this is, and the way we do this, assume the contrary, let A be great, that means A will have A plus K and A plus T, A plus L and A plus T on its sides, but it has no way of getting them if it's always switched by walnuts less than it. So that's a contradiction right there. And now we prove the converse of this, our claim 2, which is that a less walnut will switch to great walnuts. And the way we prove this is we first know one of them is great, and now what we say is, and the way we say is we know that one of A and B is great because it put K between them. Furthermore, it has to be the greater of the 2 of them, and without loss of generality, this is A. And now that means before A and B were doing the switching, we had this sort of situation, A, L, B, T, with K, L greater than A greater than B, which implies that B is also great, because which is a number greater than it. This proves our claim. And with that, we're ready to move on to our 4th and 5th claim, which are, at the end, the less walnuts will be around to great walnuts, and at the end, the great walnuts will be around to less walnuts. And now we need to prove this, and we do this by. So this is how we prove that the less walnuts will have two great walnuts at the end of it, because we know it has at the beginning, and that anytime a switch may happen, it will be from a walnut which is at less than. So that means that both of the walnuts on its sides will be greater than walnuts, which means that this initial walnut will continue having two great ones around it. And the proof for the other thing, that at the end we will have for every great walnut will be surrounded by two less walnuts. The way we prove this is, so after some playing around and trying to figure out how to actually prove this, I ended up scrapping the initial claim and realized this, that the greatness or lessness of the walnut is always deterministic. So once you set up the walnuts, you know which one are going, like it's determined which one are less and which one are great. And another thing is that this process is reversible. So say if you had walnut 1, walnut 2, walnut 4, walnut 3, and now you apply walnut 1, then you would get walnut 1, walnut 2, walnut 3, walnut 4. And now if you apply walnut 1 again, you will get the same thing back. Let's say you apply now walnut 2, and then you'll get walnut 1, walnut 4, walnut 2, and walnut 3. Now if you apply walnut 2, then walnut 1, you'll get back to the original thing. So this process goes in both ways. And now with that, we see that lessness and greatness are just opposites in a different process. If the process started from the end state with walnut 2021 and went back to walnut 1, we would have the opposites for walnuts, opposite sort of labels for what's greater and what's less. And so because of that, what we do is we make our fifth claim that at the end, not at the end, but at the beginning, the great walnuts will be around two less walnuts. And now the claim 5 follows by analogy. Just the same way we proved at the end all the less walnuts will be around two great walnuts, we have following by analogy that at the beginning we will have that every great walnut will be around two less walnuts. And now this proves this is actually enough for us to prove to get a contradiction. And the reason that is enough is now counting, we need by claim 4, for every less walnut, we need a great. And in fact, this means that there will be at most 1,010 less walnuts. And by analogy, at most 1,010 great walnuts. But given that or if you want to put it another way, you'll have at most 10 less walnuts, which means at least 11 great walnuts. And then you'll have that you have at most 10 great walnuts, which is a contradiction. So our initial claim that every single walnut will be either a less walnut or a great walnut led us to a contradiction. And this solves our problem. And as always, thanks for problem solving.